All right, so now we're going to talk about rational functions. Now, don't get upset, but the word rational means a fraction, okay? A fraction. It's a polynomial over a polynomial. And when we have fractions, that's when we run into these vertical asymptotes. But now we're going to get a little more in depth about asymptotes because we're going to get more complex rational equations given to us. So this is an example of a graph of a rational, and these dashed red lines are asymptotes. So just as a review, this dashed line is your horizontal asymptote, and so its equation would be y equaling 1, right? It's up 1. So your horizontal asymptote will always be y equals a number. So you'll have horizontal asymptotes in addition to vertical asymptotes. This red dashed line is a vertical asymptote, and it's going to be x equaling what? X equaling 3. All right, so when I said you've got to know how to write equations of vertical and horizontal lines, here's where it comes up again. Okay, so you need to be very good at this. All right, so vertical asymptotes are equations in the form of x equaling a number, and that occurs when the denominator of your fraction is 0. Okay, a vertical asymptote will occur when the denominator of your fraction equals 0. Your graph of your function, when you actually graph these functions, they will never cross a vertical asymptote, ever. Okay, so when you have an asymptote, your line will get really close to the asymptotes, but it will not cross them. It will do what we call hug an asymptote. Okay, so when you graph your function, it will hug the asymptote, but it will not cross it. It will get closer and closer and closer to it, but not cross it. Okay, so the easier asymptotes are the vertical asymptotes, and let's just jump right in and take a look at this example. It says identify the vertical asymptotes if there are any, and then sketch it. Okay, vertical asymptotes come from the denominator of your rational function. What values will make that denominator equal 0?
X minus 4, x plus 4.
Well, okay, so if you factored it, it would be x minus 4 times x plus 4. But in other words, x cannot be 4 and x cannot be negative 4 in this domain of this function, right? So your vertical asymptotes are going to occur at the points where the function cannot exist. So when we talk about vertical asymptotes, we just write VA for vertical asymptotes, and there's two of them. One is the vertical line where x equals 4, and the other is the vertical line where x equals negative 4. So those are the equations of your two vertical lines, which are your two vertical asymptotes, which is where that function is undefined when you plug that number in. So when you draw a vertical asymptote, we always draw them as dashed lines. In other words, they're going to be guidelines to the actual graph of f of x. And your graph f of x will never cross a vertical line, a vertical asymptote. It'll never cross a vertical asymptote. Now, I've noticed in your homework, they also are going to ask the question, what is the domain of this function? And it would be every real value, but not 4 and not negative 4, right? So it's all real numbers, but x cannot be 4 and x cannot be negative 4. So in interval notation, it would be negative infinity to negative 4, negative 4 to 4, and 4 to infinity. So they're kind of throwing that in as part of some of your homework questions is what is the domain. Okay, so I'm not even graphing my function. I'm only looking at the vertical asymptotes of this function at this time. Okay, so let's go down to the next one. Again, talk about, we're not going to graph it, the function itself, just the vertical asymptotes to the function, and talk about the domain. Okay, so on this one, what would cause this denominator to equal 0, which would make the function undefined at those numbers? Okay, well, if you can't just pull it out of your head, which would be really hard to make it up, then go ahead and say, what in the world will make this equal 0? Well, factor it. If I factor it, if it's in factored form, now it's real easy to see what two numbers are going to make the denominator 0, right? What are the two numbers? 3 and negative 1. So x cannot be 3 and x cannot be negative 1, or the denominator of this rational will be 0 and the rational will be undefined at those locations. So those places where the function is undefined are the places where you will have vertical asymptotes at x equaling 3 and at x equaling negative 1. So if I graph my vertical asymptotes, not the function itself, but just these asymptotes that will be guidelines to my graph of my function in a few minutes, there are the two vertical asymptotes. And then kind of off to the side, they ask this question, what is the domain of this function? Well, it's all real numbers, but you better take out the 3 and you better take out the negative 1, because those are the two values that make it undefined, which also create vertical asymptotes. And so this would be negative infinity to negative 1, negative 1 to 3, and 3 to infinity. That would be the domain of this rational function. Okay, moving right along. This next example, again, when they ask for vertical asymptotes, you want to know what values make the denominator equal 0, which in turn makes the entire rational undefined. Are there any values that would make this denominator equal 0? Well, let's try that. If I put a 5 in there, is that denominator going to equal 0? That would be 25 plus 25. Okay, so would negative 5 do it? No. So actually, it's because of this plus sign right here that it's not following in the pattern. Had it been a minus sign, you would be right on track with those numbers. But with the plus sign, there are no numbers that make it undefined. So there are no vertical asymptotes. I think I just spelled that wrong. I got close. No vertical asymptotes, and the domain, there's no restrictions. It's all real numbers because there are no values that would make that denominator equal 0. And that's all based on the fact that there's a plus sign between that x squared and that 25. Had it been a minus sign, it would have been some vertical asymptotes. Okay, so that's just a warm-up to vertical asymptotes. So you know from the original graph that we also have these things called horizontal asymptotes. Why is this not scrolling? There we go. Okay. We also have horizontal asymptotes. So right here. Here comes the next one. Horizontal asymptotes are y equals a number. And we're also going to run into these things called oblique asymptotes. Well, this textbook really does not use in that word oblique, which most books use. This textbook, just so you know, refers to this as a slant asymptote. I've heard of that informally, but I've never seen them actually use it consistently in a book. So I usually call it an oblique asymptote. Horizontal asymptotes are usually the acronym HA, and oblique is OA, so that we don't have to write that word asymptote over and over again. All right. So the line y equaling a number is a horizontal asymptote, etc., etc. But look at this note. Your function might cross a horizontal asymptote or an oblique asymptote. You never cross a vertical asymptote, but you know you would cross a horizontal or an oblique. So in the back of your mind, be aware that that can happen. All right, so how in the world do we find horizontal asymptotes and oblique asymptotes? All right. It's all based on the degree of the numerator and the degree of the denominator. For this first example, the degree of this numerator is a second degree polynomial. And the degree of this denominator is a third degree polynomial. So there's a rule that you memorize that says if the degree of the numerator is less than the degree of the denominator, and so they claim this to be n and this to be m, so if the numerator is of lower degree than the denominator, then immediately by memorization, you have a horizontal asymptote of y equaling 0. So this is something you memorize. If the degree of the numerator is less than the degree of the denominator, you have a horizontal asymptote of y equaling 0. If I was to graph y equaling 0, where would it be? It's the x-axis. Right here is the line y equaling 0. It is the x-axis. Okay, so this next example, still in this same part A, note that the degree of the numerator is 2 and the degree of the denominator is 3. So again, if the degree of the numerator is less than the degree of the denominator, by memorization, you immediately have a horizontal asymptote at y equaling 0, which is the x-axis. I might put in parentheses here the x-axis. All right, so that's the way you get a horizontal asymptote, is if the degree of the numerator is less than the degree of the denominator. Well, there's another way to get a horizontal asymptote here in part B. But this one says if the degree of the numerator equals the degree of the denominator. Okay, we'll take a look at this example. The degree of the numerator is a third degree polynomial, and so is the degree of the denominator. It is also a third degree polynomial. So if the degrees are the same, if the degrees equal, then the fraction created by the leading coefficients will give you your horizontal asymptote. So in other words, your horizontal asymptote is y equaling 3/7 for this example. Again, it's a memorization. So y equaling 3/7 would be less than 1, be almost a half. So you'd have a horizontal asymptote like this one that I'm sketching. Right here would be your horizontal asymptote of y equaling 3/7. Almost a half. All right, another example of that same condition. Looking at this example, the degree of your numerator is 5, and the degree of your denominator is 5. These largest exponents on the x variable, and they should always give these to you in descending order, so it should be that leading term. So in this case, when the degree is the same, we come up with the horizontal asymptote using the leading coefficients of the numerator and the denominator. So your horizontal asymptote is y equaling a negative 6/3, which is what? Y equaling what? Y equaling a negative 2. So this is really a bunch of memorization, and I'll give you a little bit of a cheat sheet for this on the test, so don't panic about having to memorize so much stuff. This would be a graph, a sketch of the horizontal asymptote of that second example. Okay. So we've talked about vertical asymptotes, and we've talked about horizontal asymptotes. Verticals are all based about the denominator. Horizontal asymptotes, if the degree of the numerator is less than the degree of the denominator, it's the x-axis, y equaling 0. If the degree of the numerator is the same as the degree of the denominator, it is that new y equals number of the leading coefficients. Okay, now one more thing. What if the degree of the numerator is exactly 1 greater than the degree of the denominator, like this one? What if the degree of the numerator is more than the degree of the denominator? 1 more than the degree of the denominator. That's what throws us into the oblique or slant asymptotes. If the top is of higher degree than the bottom, you have a slant asymptote or an oblique asymptote, whatever name they're using it according to the book you're in. So how in the world do I come up with a slant asymptote? This is where you go into division. Now, I'm thinking that we can avoid long division on these. If I have to actually divide this x minus 2 into this 3x squared minus 4x minus 1, that's not very fun. We've already learned that that's, we can do it, but it's kind of long. So since the degree of the denominator is a first degree equation, we can come in here and do synthetic division. 3x squared, negative 4x, negative 1. drop the 3. So we're going to do synthetic division because the denominator is a first degree expression. 2 times 3 is 6, add. 2 times 2 is 4, add, and you get a remainder. Now when you're finding your oblique or slant asymptote, you don't worry about the remainder because it's such a detail that you're not going to be able to graph that kind of detail. So we come up with an equation y equals 3x plus 2. And this is your oblique asymptote. So it's not a simple horizontal line, it's a diagonal, slanted line. Slanted straight line as an asymptote. So if I had to graph that asymptote, that linear equation, I would very quickly pull a couple of points on this line. When x is 0, y is 2. When x is 2, it would be 8. So 0, 2 is here. 1, 2, 8 would be a little high off the screen, but this would be a slant asymptote. Okay, there would be a slant asymptote, and it should be straight. Okay, mine's not exactly straight. It's kind of hard for me to get a straight one, especially on a tablet. But I tried. So there it is. You have 3 types of asymptotes. Vertical, which are based on the denominator. Horizontal, the degree of the numerator is either less than or equal to the degree of the denominator. And now oblique, where the degree of the numerator is more than the degree of the denominator by 1. All those asymptotes. And I know that that's going to be hard to memorize, so you might want to make a little card or keep these notes close by. Okay, keep them close by. All right, so let's see what's next. Identify the asymptotes. They don't even have vertical on here, but we should. Okay, vertical should be on here. So I'm going to put vertical on here because I like vertical asymptotes best. Okay, so with this equation, what values will make my denominator equal 0? 3 and negative 3, right? Okay, so I have vertical asymptotes at 3 and negative 3. And you can see them right here is where they are. There's one there, and there's one here. Okay, there's your vertical asymptotes at 3 and negative 3. Okay, now you either have horizontal or oblique. You don't get both, one or the other. It's either horizontal or it's oblique. So the degree of the numerator is 1, and the degree of the denominator is 2. If the degree of the numerator is less than the degree of the denominator, it is a horizontal asymptote where? Y equaling 0. That's by memorization. So this is a horizontal asymptote. So your x-axis is a horizontal asymptote. Here's your horizontal asymptote. Here's a vertical asymptote. And here's another vertical asymptote for this rational function that's given to you already graphed. Y'all are not smiling at me. Y'all don't look like you're having a lot of fun today. Okay, try the next one. Okay, so I'm going to start. Where are my vertical asymptotes? It's based on the denominator. 3 and negative 3 again, right? There's 2 of them. 2 numbers that would make that denominator equal 0. Now, talking about horizontal or oblique asymptote, one or the other. In this case, the degree of the numerator is 2, and the degree of the denominator is 2. So they equal, so there's a horizontal asymptote at y equaling 3, the 3 over 1. So you have a horizontal asymptote of y equaling 3. This graph is a little bit jogged, but here would be your 2 vertical asymptotes at 3 and negative 3. And then at y equaling 3 would be your horizontal asymptote. So you can kind of see how the graph is working around all of your asymptotes. Okay, how the graph is working around all of your asymptotes. Okay, take a look at this one. Once again, we still have the same denominator, so the vertical asymptotes are at 3 and negative 3. And now when we look at the degree of the numerator and the degree of the denominator, what is this one? This is the oblique asymptote, the slant asymptote, right? The slant asymptote. And this is not linear. This is not a degree 1. So I cannot use synthetic division. I cannot use synthetic division because it's not a first degree denominator. So this is where you literally would have to take x squared plus 0x minus 9 and divide it into 3x cubed plus 0x squared plus 0x plus 0. You cannot shortcut this into synthetic division because it's not a first degree divisor. And this is a really weird division. X squared goes into 3x cubed, 3x times x squared is 3x cubed, 3x times 0 is 0, 3x times a negative 9 is a negative 27x. Then when you come in here and you change your signs, change, you get a remainder of 27x. And when you bring down the plus 0, that does nothing. And that's like your remainder because x squared won't go into that. And so you stop, and so your oblique asymptote is y equaling 3x. You don't worry about the remainder. It's like y equaling 3x plus 0. But just leave it as y equaling 3x. And so now when you graph these, your vertical asymptotes are here and here. Your lines, your graph is not crossing them. And your oblique asymptote is the slant line coming up like this. There's your oblique. So this oblique one is your y equaling 3x line. This is your x equaling negative 3 vertical asymptote and your x equaling positive 3 vertical asymptote. So I know you must be feeling overwhelmed at this moment, but I promise it gets better. It gets a little better when we do some examples. The oblique asymptote is the most difficult one. Okay, so don't panic on me. Do not panic. Okay, one more thing I have to show you before we finally really get to do some true examples. There's a case of a graph in which your graph might cross your horizontal asymptote. Actually, it could also cross your oblique asymptote. And so I need to show you how to do it. And then when we finally get to an example, it will make sense what you're doing. You won't be so lost. All right? So in this example, we're going to have, let's talk about all the asymptotes. Okay? So your vertical asymptotes will occur when the denominator equals 0. So you need to factor this thing in order to come up with your vertical asymptotes. And the denominator factors into x minus 4 times x plus 1. So you're going to have a vertical asymptote at x equaling 4 and another one at x equaling negative 1. Like this. Here's your x equaling 4 vertical asymptote, and here's your x equaling negative 1 vertical asymptote. Your graph will never cross a vertical asymptote. Now, when I either have a horizontal asymptote or an oblique asymptote. One or the other, not both. The degree of the numerator is 2 and the degree of the denominator is 2. So if the degrees are the same, you have a horizontal asymptote, and where is it?
2.
Y equaling 2. That is the ratio of the leading coefficients 2 over 1. So right here is your horizontal asymptote. Okay, you will never cross your vertical asymptotes, but this function, when graphed, might cross a horizontal asymptote. It might cross it. So to determine if it's going to cross it or not, does my f of x cross my oblique, it's not oblique, it's horizontal asymptote. Does it cross my horizontal asymptote? That's my question. Well, the way you determine that is you set your original function equal to your horizontal asymptote. So I'm going to set my f of x equal to my horizontal asymptote. My f of x is 2x squared minus 4 over x squared minus 3x minus 4. My my horizontal asymptote is y equaling 2, so I put the 2 here. So I set them equal to each other. That's how you determine if they're ever going to cross. Well, the way you solve this is you write your horizontal asymptote, or your value of 2, as a fraction, and then you cross multiply. Okay, then you cross multiply. So 1 times 2x squared minus 4 is 2x squared minus 4. And then you have 2 times your x squared minus 3x minus 4. So this becomes 2x squared minus 4 equaling 2x squared minus 6x minus 8. Now, pretty much in every case you'll see, when you come in here and you subtract your x squared term off of each side, this becomes a lot easier. This will then become negative 4 equaling 0 minus 6 minus 8. Then when you add 8 to each side, you get positive 4 equaling a negative 6x. And then when you divide by negative 6, you get a negative 4/6. So yes, f of x crosses the horizontal asymptote at x equaling, well, negative 4/6, which is a negative 2/3. Okay, so now what I've done is I've given you the foundation, a combination of a million details so far, just trying to prep you for actually graphing a rational function. Okay, so now you have just the basic skills to really jump in and graph one of these rational functions. Okay, so now you're ready to actually graph something. Okay, I know it's kind of exhausting. You're like, oh my gosh, I'm so overwhelmed. You just have to be patient. They give you a procedure here, all of these steps. You start by finding your vertical asymptotes, then you find your horizontal or oblique, then you find your intercepts, and then the optional part is all the symmetry. Now, I put here in part E, in red, in Connect Math homework, you are not required to graph. That's because they cannot give you electronically a piece of graph paper and let you freehand a graph. But they're going to ask you all the details. They're going to say, what are the vertical asymptotes? What are the horizontal asymptotes? Do you cross them or not? What is your x-intercepts? So you're still going to have to go through all the algebra I'm showing you, but you're never going to get to graph it in Connect Math. So we are going to graph it, and you're going to want your calculator to do this. Okay, you're going to definitely want your calculator in these. So what I wrote here was be sure you can use your calculators to confirm your graph. All right, so we're going to be using some calculator graphs here. All right, so here we go. Let's jump in and try to graph one of these things. The first thing we want to do is take a look at vertical asymptotes. Okay, we want to look at vertical asymptotes first. And the vertical asymptotes are pretty independent of everything else because they rely on the denominator. Well, to get the vertical asymptotes, I need to factor this denominator. And it's going to factor into an x minus 6 times an x plus 1. Normally we would factor the numerator too, but we really don't have to. I'm going to go ahead and do it. You don't really have to factor the numerator. It's the denominator you're focusing on, but you could factor this numerator also. Okay, so your vertical asymptotes are going to occur at x equals what? 6, and the other one is x equaling negative 1. Those are the equations of vertical lines. So over here, here's your x equaling 6. And then your x equaling negative 1. Now you will not see these lines on a graph on a calculator. They're not part of the function, they're just guidelines. Your graph is not going to cross that. It's either going to shoot up or shoot down when it comes to it. Okay, so now let's talk about, do I have a horizontal asymptote or do I have an oblique asymptote? And if I do, what is it? Okay, well, the degree of your numerator is 2, right? So you have a degree of 2 over another degree of 2, right? So that means it's a horizontal asymptote at y equaling what? 1. Because this is a 1 over 1, so it's a y equaling 1. So here's your horizontal asymptote. There's your horizontal asymptote. So there's all your asymptotes. You're through with asymptotes. Okay, so now we want to talk about where are my x-intercepts, which are what we also refer to as zeros of a polynomial. Well, your x-intercepts occur where the y value is 0. So my equation says, if I take it out of function notation, it says y equals x squared minus x minus 6 over x squared minus 5x minus 6. And I'm going to replace the y value with 0 in order to come up with my x-intercepts. Now at this point you're probably thinking, I have no clue how to do this algebraically. Absolutely no idea. But it's not difficult because all you need to do is once again cross multiply. So put your 0 over 1, and when you cross multiply, you'll get 0 equaling 1 times x squared minus x minus 6. Right? Because 0 times x squared minus 5x minus 6 is 0 on the left side. Then what am I supposed to do? You're supposed to factor it. You're supposed to pray this sucker factors, because if it doesn't factor, you're going to have to go to the quadratic formula, which takes time. It's not difficult, it's just time consuming. Then you set each one of these factors equal to 0, and you get your x-intercepts occurring at 3 and negative 2. Okay, so you have 2 x-intercepts. They occur at an x value of 3 on my graph. Here's my 3, 0 on my graph, and at negative 2, 0 on my graph. Okay, so check mark. I've found my vertical asymptote, my horizontal asymptote, and I've found my x-intercepts. Now I'm supposed to try to find my y-intercept. Do I have enough room here? Oh, yeah.
On the question we just did, whatever happened to the 1 times x squared minus 5x minus 6?
It's not a 1, it's a 0. When you cross multiply, like this, right? 0 times x squared minus 5x minus 6 is 0. And then 1 times this one is x squared minus x minus 6. Okay? All right? Okay, very good. So now we need to find our y-intercept. Our y-intercept occurs when our x value is 0. So going back to my equation, which is so high on the screen I can't even see it, but it is y equaling x squared minus x minus 6 over x squared minus 5x minus 6. When I replace my x value with 0, this becomes 0 squared minus 0 minus 6 over 0 squared minus 0 minus 6, which is a negative 6 over a negative 6, which is a 1. So we have a y-intercept occurring at the point 0, 1. Okay, so I've got to scroll back up to my graph and plot this point. Okay, so I'm going to scroll up now and I'm going to plot this point. At this point, we would, right here, 0, 1, right there, bam. At this point, you would pick up your calculator and you would graph this thing. And for sake of time, I'm just going to let you know I've already graphed it on the calculator so that we're ready to do this. No, don't do that to me. Stop. Okay? And it looks like this. You're going to come in, you're going to touch that, you're going to go through that point, I shouldn't say touch it, and come down, never crossing those two asymptotes which are enclosing it. Then you're going to be up high, hugging this vertical asymptote. You're going to come down. I didn't do that very well. We're going to be up high, coming down. It's so hard to do this. We're going to swing through this point, and then come down and hug this asymptote again. So did we cross our horizontal asymptote? Whoa, we sure did. We crossed our horizontal asymptote right there, which is another algebraic step we need to do. And then on the outside over here, we are up above, coming like this, and then going out. That is what the graph looks like. Well, it looks a little better than that when you draw it not on a tablet, okay? But you will see this on your calculator. Now, just to let you know, when you're on your calculator graphing this thing, on your calculator, it's going to look like y equaling on your calculator, so you know how to type this in. On your calculator, it's going to be y equaling parentheses, your numerator, divided by parentheses, your denominator. You must put the numerator in parentheses independent of the denominator to graph it. And this should look pretty good in just a zoom standard window. So if you just do a zoom standard, you should be able to catch this graph that I have tried to draw up here on this tablet. Okay, so we did a lot of things, but we didn't get a chance to talk about how to find the point of intersection of the horizontal asymptote and the graph itself. And I think I can do it in this little bit of space right here. So hold on, let me write this better. F of x crosses my horizontal asymptote. And to find where it crosses it, I set my function equal to the value of my horizontal asymptote. So this would be my x squared minus x minus 6 over x squared minus 5x minus 6 equal to my horizontal asymptote, which was y equaling 1. Okay, your horizontal asymptote was y equaling 1, and you put that 1 in this equation. Then when you cross multiply, you'll get x squared minus x minus 6 equaling x squared minus 5x minus 6 when you cross multiply. Then you're going to subtract off your x squareds, and get your negative x minus 6 equaling a negative 5x minus 6. Then when you add 5x to each side, you'll get 4x minus 6 equaling a negative 6. Then when you add 6 to each side, you'll get 4x equaling 0 or x equaling 0. So you're going to cross at an x value of 0. And that x value of 0 is going to give you the point 0, 1, where your function crosses your horizontal asymptote. And I showed it when I'm graphing up here. I go, woo, there it is, and highlighted it. That is the point, 0, 1. Okay, so I've got to close this recording, and I'll leave this up here so you can write it down, because I know you're trying to get it written down. But I need to go ahead and close this recording.